For over 200 years, physicists thought they had basically figured out everything. The laws of motion worked perfectly. Planets moved exactly as predicted. Light, electricity, magnetism, it all seemed to fit into one complete picture. It looked like the universe was completely understood. But then a series of experiments started giving results that made absolutely no sense. This is the breakdown of classical physics and how those failures led to the birth of quantum mechanics. For over 2 centuries, classical physics dominated science. Newton's laws didn't just explain motion on Earth, they explained the motion of planets, moons, entire solar systems. The same equations that described an apple falling could describe the orbit of a planet. Then, in the 1800s, Maxwell unified electricity, magnetism, and light into a single theory. Suddenly, things that seemed completely different were actually the same phenomenon. By the end of the 19th century, physics looked incredibly complete. The universe appeared to follow precise, predictable laws. In principle, if you knew the exact state of a system, you could predict the future perfectly. But that confidence didn't last. The first cracks in classical physics started to appear when scientists began studying atoms. In experiments with cathode rays, scientists observed a stream of particles moving through a vacuum. These particles could be deflected using electric and magnetic fields, which meant they had charge. This led J.J. Thomson to a major conclusion. Atoms weren't indivisible after all. They contained smaller particles, what we now call electrons. But the structure of the atom turned out to be even stranger. In Rutherford's gold foil experiment, alpha particles were fired at a thin sheet of gold. Most of them passed straight through, as if the atom were mostly empty space. But a small number were deflected at very large angles. Some even bounced straight back. This was completely unexpected. It revealed that the atoms contain a tiny dense nucleus at their center. But this created a serious problem. According to classical physics, electrons orbiting a nucleus should continuously lose energy and spiral inward. So why don't atoms collapse? One of the biggest assumptions in classical physics was that the universe is completely deterministic. In theory, if you knew the exact state of a system, every position, every velocity, you could predict the future perfectly. Nothing was truly random. If something looked random, it was only because we didn't have enough information. But experiments at the atomic scale began to show something very different. Some events didn't just appear random. They were fundamentally random. Even with complete information, you couldn't predict the exact outcome of a single event. You could only predict probabilities. This was a huge shift. It meant that randomness wasn't just a limitation of our knowledge. It was built into nature itself. In classical physics, if classical physics were correct, electrons orbiting a nucleus should be able to have any energy. That means atoms should emit light across a continuous range of wavelengths, basically a full rainbow. But when scientists actually looked at the light emitted by atoms, they saw something completely different. Instead of the continuous spectrums, atoms emit light at very specific wavelengths. The result is a set of distinct lines, almost like a fingerprint unique to each element. Classical physics had no explanation for this. And this also connects back to an earlier problem. Why don't atoms collapse? According to classical physics, electrons should continuously lose energy and spiral into the nucleus. But these discrete spectra suggest something very different. Electrons can only exist at specific energy levels. They don't lose energy continuously. They can only jump between these allowed states. And that's what produces these discrete lines, these discrete spectral lines. Up to this point, light was understood as a wave. And according to classical physics, the energy of a wave depends on its intensity, basically how bright it is. So if you shine light on a metal surface, increasing the brightness should give electrons more energy. But that's not what happens. Experiments showed that electrons are emitted instantly, but only if light has a high enough frequency. Increasing the brightness doesn't increase the energy of the electrons, it just increases how many electrons are emitted. And if the frequency is too low, no electrons are emitted at all. Classical physics couldn't explain this. The only way to make sense of it is if light doesn't deliver energy continuously, but instead comes in discrete packets. Each packet carries a specific amount of energy determined by its frequency. These packets are what we call photons. Up until now, we've treated electrons as particles, small, localized objects that travel along definite paths. So if you fire electrons at a barrier with 2 slits, you'd expect them to go through one slit or the other, and form 2 distinct impact regions on a screen. That's the classical prediction. But when the experiment is actually performed, that's not what we see. Instead, we get an interference pattern, the same pattern you would expect from waves. bright and dark bands formed by constructive and destructive interference. And it gets even stranger. Even if you send electrons one at a time, the interference pattern still builds up over time. It's as if each electron is interfering with itself. Classical physics has no way to explain this. The only conclusion is that electrons, things we thought were particles, also behaves like waves. Matter itself exhibits wave-like properties. By the early 20th century, classical physics had pushed incredibly far. It explained motion, forces, electricity, even light. But as we've seen, it started to break down at small scales. It couldn't explain why atoms are stable, why spectra are discrete, why light behaves like particles, or why electrons behave like waves. These weren't small issues. They were fundamental failures. The assumptions of classical physics, continuity, determinism, clear particle behavior, were no longer enough. A completely new framework was needed: quantum mechanics. In this new picture, energy is quantized. Outcomes are inherently probabilistic, and matter and light both exhibit wave-particle duality. It didn't just fix a few problems. It completely changed how we understand reality. And just quickly, all images and diagrams are properly credited here. Thanks for watching.